Hey, math people. Let's build some graphical intuition. What I have in front of me is the SAT practice test number 1. It's the first one. So you can type in practice test, practice SAT, enter the very first test. And I have the calculator portion. I want to take a look at that. I want to build some graphical intuition with you guys. So what I did was I looked through, and there's my cursor. I looked through this test and I found all the problems that could have in some capacity relied on the graph. So what I have I'm going to kind of skip through a few of these. What I have ready is the graph for those 9 problems. I chose 9 problems that very much rely on the graph. So let's build some graphical intuition together. Some of these problems, you probably shouldn't actually look at the graph if you know the algebra behind it, but it's nice to be able to visualize what's happening in the background with that graphical piece. So that's what I want to do with this video is I want to challenge you to think about some of these problems graphically. Because sometimes if you can just kind of like tilt your head and think about what the graph looks like, that can go a long way and save you quite a bit of time. So let's build some graphical intuition with one another. Okay, so we're looking at the calculator portion. So that's like the 4th test, right? On the SAT for practice test number 1 that you can find just by Google searching that on College Board's page. Okay, let's do this. So the very first problem is right off the bat, number 2. This problem, I will say, you should probably do this one algebraically, but I do want to at least show you what it looks like graphically so we can at least build that understanding. So how about I do that? How about I show you this graphically first, and then I'll show you probably the most optimal way. Make that connection, bridge that gap. Okay, so if y is equal to kx, where k is some constant, and y is equal to 24 when x is equal to 6, what is the value of y when x is equal to 5? This can be a plug and chug, but I want to show you that there's some fun math moving on in the background. So I'm on Desmos, and I do want to just use this as like a secondary purpose to also kind of show you how Desmos works. If you type in y's and x's, it's going to assume, you're on the xy plane. It's going to assume x is your horizontal axis, y is your vertical. So any other letter, though, it's going to say, hey, do you want to add a slider for it? And I shouldn't say any other letter, right? Because E is a constant. So most of the other letters, certainly K, we can use as a constant value. And what's nice about Desmos, it allows you to use a slider. And a slider is just something where if I manipulate this K value, like right now it's 1.5, it has a slope of 1.5. Now it has a slope of 2.6, 5.1, so on and so forth. So you can kind of slide it back and forth, and you can see what happens to the graph visually. This is a basic line. I was going to call it a linear line, but all lines are linear, right? So we don't really need to access this graph, but it's a lot of fun to play around with it, because if I had an x value of 6, which you can see I've already entered that in, and if I have a y value of 24, those two moments intersect right here, 6, 24. What I can do is I can just kind of line this up and see when this is true. When am I going to have a k value where this equality holds true? It's going to be when they intersect. So if I just kind of keep moving, achoo. Okay, I skipped over it, right? Right around here, right when your k value is 4. And this should make perfect sense, right? So if I show you can see I was looking at the answers. A little cheating. I'll exit out of that one. You can see algebraically, I can plug in a y value of 24. I can keep my k, and I can plug in an x value of 6. One-step equation, right? You get a k value of 4. So it should make sense. I have y is equal to 4x. Plug in your 5. Okay, you get an answer of 20. But as you can see here, the graphical intuition meets the algebraic computation. When I hit an x value of 5, you better believe what's going to shoot out is that y value of 20. So for this first one here, answer is C. Was this optimal to look at the graph? No, not at all. But try to see, as we go through these problems today, see things visually, both through the lens of like, hey, maybe play around on Desmos every so often, and it's just a way better platform to look at graphs. And also as you're moving through the problems, think about like what shapes you're manipulating when you're performing some algebra on it. So for the first one, I would not have done that, but for the rest of these, it's going to be a little bit more relevant. So looking at 10, we are given, it's one of those like questions in 9 and 10 refer to the following information. we're given a linear equation. So think about your y is equal to mx plus b kind of stuff. I'll actually kind of show you that this is a familiar friend. I know that it's with an a and a t, and your b values kind of flip-flopped with m. But always look for these opportunities to connect it to something you did back in math class. Because you would be surprised how many questions hinge on our good friend y is equal to mx plus b. It's an enormous number of questions. I pretty much tell, like I teach calc, and I pretty much tell these calculus kids, like, yeah, you're taking like mostly an algebra 1 test. And the reason why, it's accessibility, right? Not everyone gets up to calc in high school. It's a good, it's a fair assumption to say everyone has seen like algebra 1, so that's why you see a lot of these style of questions, especially early on. Anyway, so we're given this y is equal to mx plus b, and it looks like the speed of sound waves in the air depends on the air temperature, okay? The formula above shows the relationship between a, the speed of a sound wave in feet per second, and t, the air temperature in degrees Fahrenheit. So with 10, it does ask, at which of the following air temperatures will the speed of sound be closest? So right off the bat, it's going to be an approximation to 1,000 feet per second. Know what goes in and what shoots out. So looks to me like T is what goes in, and T is the air temperature. So in goes temperature, and then out shoots, what is the A value? Speed of sound in feet per second. So I'm just going to write like feet per second here. In goes temperature, out shoots the speed of sound, feet per second. And it's looking for the temperature. So we know the output is 1,000. So we want to set this equation equal to 1,000. So this would be the algebraic approach. And I just want to make sure I write it down properly. 1,052 plus 1.08. You can put x, you can put t, it doesn't really matter here, because at this point you're just solving for it. This would be the way to solve it algebraically, so I will finish this off in a second, but I do want to go to the graph. And again, an excellent opportunity for me to kind of just sell Desmos as like a platform. You should do your graphing on Desmos whenever you're at school. I just can't fiddle around with those TIs anymore. Let's welcome the day Desmos is our primary calculator device. So what's nice about Desmos, right now I don't see my graph. I actually do have it graphed here, right? You can see it as the equation. I have to zoom out a lot in order to see it. And what's intuitive about the zoom out process, you literally just scroll out. But let's just say I wanted to get there in a like a windowed based approach. I would think about what values would I need to plug in for x and for y to see this graph more locally, because as of right now it's not on the screen at all. So it looks like to me my y-intercept's 1,000. I'm going to challenge you here. Try to think about what is a reasonable x in lower x bound. So sorry, x goes this way. A lower x bound, an upper x bound, a lower y value bound, and an upper y bound. Because that kind of like thinking can save you time not only in your normal math class, but it builds a number sense. So if your y-intercepts at 1,052, you should probably make your lower y bound quite large in order to see it. Let's make it like 1,000. And then maybe I'm just interested, and I can zoom out. So maybe I'm interested in the first few values. So I'm going to go to like 1,200. So right off the bat, I can already see it. If I want to manipulate the x values, maybe I'm not too concerned with these negative values, because if we go back to the problem, in goes degrees Fahrenheit and out shoots feet per second. So we're probably not going to be playing around with like, I guess we can be playing around with negative values, right? Because we have negative values here. So maybe I'll just leave the x values as is, and I can just kind of zoom out if I need to access values on the left or values to the right. We're trying to find when we have a y value, an output of 1,000. So I'm going to write out y is equal to 1,000. And I'm trying to figure out when these two lines intersect. So maybe this is when I can manipulate our x window. Sure, I can just scroll and I can find it right here. And maybe that's the way to go, but I guess the old-fashioned like TI version of me wants to type it in as x is equal to. So maybe I should let that go, huh? Maybe I should just scroll. Anyways, I'm just going to scroll, figure out when they intersect. And sure enough, right over here, at an x value of negative 48-ish. So I did mention earlier that this was going to be an approximation-based problem because it does ask, there's a key word in here, which of the following air temperatures will the speed of sound be closest, meaning round. So we see here that negative 48 is definitely our answer. And I can solve this algebraically too. So again, point of this isn't to find optimal ways of solving these problems, but to build an understanding of what you're doing graphically. So what is the algebraic process to this? You subtract 1052. You get negative 52 is equal to 1.08t, and divide both sides by 1.08. What's also nice about Desmos, I feel like an ad man for Desmos, is that you can do basic computation in here as well. So negative 52 over 1.08, negative 48.14, and sure enough, same exact point of intersection there. Yeah, it's wild. It's like I have every urge to use this x and y window because it's like the old school version of me. I will say sometimes it is practical though, because it does help you change your y scale or your x scale. Like here you can see these values go up by 100, where these values just go up by that standard 5. So it can be helpful, but wasn't really worth our time for this one. So 10's looking like B. Let's move on to 18. That's the next one that I kind of deemed is like graphing and Desmos worthy. Okay, so we're looking at a system of inequalities, and we have these unknown y-intercepts. One is labeled as A, and one of them is labeled as B. Desmos is great for this, so I'll head on over it to right now because I can add sliders for both of these. So there's A, there's B. Right now they're both set to be exactly 1, and I can slide them however I please, and you'll see some kind of cool movement for it. So I'll just kind of default set them back to 1 for now, so we haven't finished reading the problem. Okay, so in the xy plane, if 0, 0 is a solution to the system of inequalities, which of the following relationships between A and B must be true? So I have some inequality statements, and one's an equation. Okay, so the way that you find solutions to systems of inequalities is it should be in the double shaded region. So I'll turn off orange for a second here. This is purple, so a solution for just an inequality is you're in the purple. And if I turn on orange, a solution for you to be, or a way to be a solution for just this inequality here is to be in the orange shaded region. So if we want a solution to a system, we have to be in both shaded regions. So I guess purple and orange, if you intersect those colors, you get like a reddish color. So what's nice about Desmos though is that I can change the colors if I'd like. So I don't know, I'll change to green. Maybe we'll do blue and orange, purple. Having too much fun with this. We'll do green and blue. All right, so what am I interested in? 0, 0? Yeah, so I want 0, 0 to be in the double shaded region. So I will map 0, 0 because Desmos has a feature for that. We'll make this a black point and I'll label it out. So as of right now, is 0, 0 in the double shaded region, the intersection of both blue and green? No, it's in just green. So A is equal to 1, B is equal to 1 when they're both the same value. Fortunately, I can't cancel anything out from that, but let's just play around with the slider. Let's make A smaller than B. All right, so when A is -2 and B is 1, definitely not a solution. So when A is smaller than B, that's no good. Canceling out choice B here. All right, what about when we have some absolute values? So I actually think we can cancel out C as well. No, we can't. How about we do... now we can. If I have a B value of 4 and an A value of -2, is it true that the absolute value of -2 is greater than absolute value of 4? No. I don't like the way I crossed that out. There we go. What about when I make B the negative version of A? So as of right now, A is -2. I'm just going to make B 2. Is 0, 0 in the double shaded region? Again, no. I plugged in, what did I have? I had -2 for A and 2 for B. So I satisfied the criteria, yet definitely not in the double shaded region. We're forced into choice A. So A must be greater than B. Let's play around with the situation where that's true. And I'll make B pretty far negative. I'll make A pretty far positive. Definitely true. I have 0, 0 in this like teal region, this double shaded region, not in just the blue, not in just the green, but in both. And A is greater than B here. So we have ourselves a winner. If I didn't have access to Desmos here, I would probably just play around with numbers. I would plug in values to see what works and what doesn't work and what satisfies the inequalities. I would say Desmos is the better way to go, though, if you can use it. Maybe one day you can. In 2022, right now, you can't. Anyway, guess and check, plug and chug is the way to go. I like the visual take on it. 18 is down. Let's look at 24. Please no reading. Okay, good, no reading. So which of the, a little bit. Which of the following is an equation of a circle? So you need to know your equation of circle. It looks like this. X squared. Well, if it has a shift to it, then I'll write it out that way. X minus h squared plus y minus k squared is equal to r squared. So h and k is your center, and r is your radius. Okay, and I guess I just assumed everyone knew line. So the last few problems we did were mx plus b, where m is your slope and b is your y-intercept. So if you didn't, the ones that I just did, if you didn't register that, then you gotta go back to the fundamentals there. All right, so which of the following is an equation of a circle in the xy plane, center 0, 4, radius? Okay, so it's got this crazy 4/3, 5 like endpoints. So we have to find the radius because they're giving us h and k. They're just giving you h, they're giving you k. So you can actually just plug these in. Algebraically, this is how I would solve this problem. I would do like x minus 0 squared plus y minus 4 squared is equal to r squared. And this just exists on my curve. So I would plug in 4/3 for x and 5 for y. And then I'd solve for r. 4/3 squared plus, so 5 minus 4 is 1. 1 squared is equal to r squared. I'll just finish solving it out the lame way, the algebraic way, and then I'll show you the graphical intuition behind it. This is 16 over 9 plus 1 is equal to r squared. And 1 is the same thing as 9 over 9. Agree, right? 9 over 9 is 1. Because I can add across the top now. I get 25 over 9 is equal to that r squared value. And I don't even have to solve for r because within the equation, it's r squared. So I just need the choice with 25 over 9. Looks like I have 2 of them. But you can't fool me. B has a plus here, and we definitely wanted that minus. So choice A is the winner for 24. Now graphically, what did you just do? Or what did we just do? We can graph a circle, and this is what a circle looks like. You knew that much. H dictates your left, right. K dictates your up, down. If you can't go from this expression and mentally think, okay, H is your left, right, and K is your up, down, that's the point of this video, is to try to help you build that. And then R, think about what R is going to do. It's your radius. It's going to blow it up or shrink it, right? So what I want to do is I want to try to find the center of 0, 4. So I'm going to make H 0, 0, and K 4. Okay. So as of right now, and I also graphed the endpoint 4/3, 5. It's right here, and I'll even kind of do one of those things. 4/3 is the same thing as 1.3 repeating, but I'll turn that off. So I just have to change my R value. I got to manipulate that in order to kind of figure out when I cross through that point. It looks to me like it's like roughly, whatever that 1.7, 1.6 value is. I guarantee you, watch this. When you take the square root, what was the value that we ended up getting? We got 25 over 9. You better believe what this is going to be. That 1.6-ish value. So how about I just do that? Oh, and that's fun. I'm getting closer and closer as I add more and more 6s. So perfectly touches that endpoint. Again, is Desmos or is graphing like the optimal way of doing this problem? Not necessarily, but building that graphical piece goes a long way. So A for 24. Move into 25. This one, graphically is the way to go. The equation above expresses the approximate heights. Get out of here. Shoo. Be gone. H in meters of a ball t seconds after it is launched vertically upward from the ground with an initial velocity of 25 meters per second. So that was all blah. You didn't really need to read that. You just had to read, hey, this is your height equation with time t. In goes the time in seconds. Out shoots the height in meters. After approximately how many seconds will the ball hit the ground? So ground is a height of what? That's when you screamed 0, right? Yeah, 0. So I'm just plugging in 0 here, and I'm solving. I would actually say this is just better graphically, for sure. It does say approximately, so keep in mind you're probably not getting an exact answer. So I can solve this quadratic by doing a little bit of factorization, and then I get negative 4.9. So this is the lame way. I want to do it the cool Desmos way, and then setting both of these to 0. So it looks like we have one moment of 0, which is not our solution because that's just when the ball was thrown upward. And then the other solution, so I'm using 0 product property, setting both my factors equal to 0. I would solve out this guy, and I would move the 25 over. So I'd get negative 4.9 t is equal to negative 25. Divide both sides by negative 4.9. 25 over 4.9 is like roughly 25 over 5. So answer is roughly 5 seconds. So choice is D if you do this algebraically. If I want to do this graphically, which is definitely the better way in this case on the reals, because watch how easy this is graphically. This is my equation, negative 49. I put an x because Desmos reads x as your independent variable. X squared plus 25x. And yeah, I can find all these cool things with this, right? I can find the max. So at 2.55 seconds, we have a max of 31.88. We don't need that. It's being thrown from the ground at 0 seconds from a height of 0. And when does it hit the ground? Right around 5. 5.102-ish, and that's how we got that value of 5. And this is the same exact value as, there was a circle from before, this. I can even verify for you. 25 over 4.9, bam. Okay, so answer there is D. I would say graphically is the approach for this one. You're just finding the x-intercept. So obviously on the SAT, there are questions where graphing is like the way to go. Hence why building that visual connection, important. Okay, so speaking of parabolas, let's do another. Let's do 30. We have this parabola x squared minus 2x minus 15, which looks like this on Desmos. Looks like we have a y-intercept here of 1, negative 16, which can be verified pretty easily mentally here. A little lower than negative 15. Anyway, which of the following is an equivalent form of the equation of the graph shown in the xy plane above, from which the coordinates of the vertex A can be identified as constants in the equation? That wording's kind of awkward. Usually SAT's a little bit better with the wording, but I think they just wanted to avoid saying vertex form. So you have 3 different forms for quadratics. You have this guy, let's see if I remember this. X minus h squared plus k. This is vertex form. Vertex form. Reason why, you can easily pluck out your h and your k. I meant to do that one red, but this represents your vertex. H, comma, k. So one thing I can do is I can just play around with that on Desmos. I'll show you all forms just for fun, because the point of this video is to learn after all. I can add some sliders. Looks like I already had an a value of 1, but h, think about what this does visually, right? Same thing with the circle. Left, right. K, up, down. So really we're just trying to figure out when, or what the expression looks like when I have an h value of 1, and look at this perfect fit. Whomp. I can't actually go past -10 with this current slider, but if I click this value, let's just go to -20, maybe that'll be enough. And bam, look at that fit. When I have an h value of 1 and a k value of -16, I win. So I'm just plugging those on in to my expression. So y is equal to, well, we had an a value of 1 already. X minus, I think we had an h value of 1. We had a k value of 16. It was a -16 though, right? So this is choice D. I'm going to show you the other methods though, or the other forms of quadratics. As of right now, it was given to you in standard form, which is ax squared plus bx plus c. So this is standard. And the vertex for this is wonky. It's x is equal to -b over 2a, which we clearly didn't need to know here. And then the last form, I'll just kind of sneak over here. We have intercept form. Intercept form, which is y is equal to a times x minus p, x minus q. So sometimes this form, actually you can see both of these are in intercept form, and both of these are in vertex form. So, oh no, actually C's not. C, I've never seen that form before. C's in like a kind of a goofy, I don't know what form. So really one of these was only in vertex form. This could have been like a 10-second problem where you just say, oh, you know, which of these is in vertex form, because we want to show the vertex quickly. There's only one choice. It's choice D. And the graphical intuition kind of meets that as well, which is nice. Both of these equations are the same. If you don't like these sliders here, sometimes people don't like them. I'll just go ahead and just leave this as a 1 because our a value is 1 in the standard form. Anyway, and then this was an x value of 1, k value of -16. So you can see they're the same line. I can turn these on and off and shows the same exact graph. Okay, moving on. We have 28 next. Last I check, 28 comes before 30. We're going back to 28. I think staying on the mantra of parabolas was a good idea. So anyway, 28. Looks like we have another inequality, and actually it's a system because we have two of them. So we have y is greater than or equal to 2x plus 1, and then y is greater than 1/2 x minus 1. Which of the following quadrants contains no solutions? So no shading. We already did a system before. So I'm going to find that. Here it is. So I went ahead and graphed y is greater than or equal to 2x plus 1, and I graphed 1/2 x minus 1. So we have to find when we have no solution. What quadrant has no solutions? So the way that I have it kind of colored out right now, red is here, blue is here. We want to find that like purple zone where they intersect. And definitely it's not quadrant 2. Quadrant 2 has a ton of solutions in it. Quadrant 1 has some solutions here, and then quadrant 4 has, nope, this is quadrant 3. Quadrant 3 has solutions here. So here are the solutions in 1, here are the solutions in 2, here are the solutions in 3. You're my culprit 4, you don't have any solutions. You have some solutions to just blue, but that's not enough. You need them both. So going back to the problem here, which have no solutions. This is like kind of so strange to me that they give you this. It's, in my opinion, they should almost like test you on this concept of like this like rotation of quadrant 1, 2, 3, 4. So kind of strange in my opinion that they give you it, but whatever. 4 is definitely my answer. So C, we don't have any solutions in the bottom right quadrant, which is quadrant 4. So anyway, little out of order there, but it's all good. You're alive. You've dealt with it. Okay, let's do 37 and 38. So of course we have to end the day with some free response questions. We looked at some lines, we looked at systems, we looked at inequalities, we looked at circles, we looked at parabolas. The last thing that we haven't really looked at in terms of like the definitely on the SAT graphs are exponentials. So Here we have some sort of constant value times a factor to the variable power. So Jessica opened up a bank, earns 2% interest compounded annually. Her interest deposit was $100, and she uses this expression to find the value of the account after 2 years. So we have control over X based on this information. You know what a ton of kids do here? I promise you a ton of kids do this, and that's not right. If you had 100 times 2 to the power of t, this is doubling every year in this case. So I do want to show you what I mean by that. So y is equal to 100 times 2, that's not 2, to the power of x. Yeah, and I can actually just plug in values here. If I go after 1 year, it doubles to 200. After 2 years, it doubles again to 400. After 3 years, it doubles again to 800. I don't have to keep going through the values. That is definitely not 2% interest. That's 100% interest, actually. You're doubling every year. You're at 100% of what you once were at all over again. So this is a tricky part, at least for freshmen. I just think when I teach percent interest to freshmen, it's a little tricky. If you start at $100 and you multiply it by something basic like 1, you're at 100% of what you're at. Doesn't change. But and 1 is kind of like the numeric representation of 100%, but I'm adding 2% to that. So 1% plus 2% is 102%. We're going to be 102% of what I once was after each year. How do I convert 102% to a decimal? You move the decimal place twice. So you have a value of 1.02, and that is exactly what I'm plugging in for t here, or for x, I guess. So our expression that I'm going to play around with, and I'm going to need the graphing piece for 38. So it's a back-to-back. This is our equation for Jessica, which is kind of lame if you think about it, because if you get 37 wrong, you're going to get 38 wrong. Anyway, it's going to be y is equal to 100 times 1.02 to the tth power. And I'm going to type it into Desmos to the x power, but it's going to be the same thing. So what was I trying to drive home? It is not 2. I am not doubling every year. I'm going up by a factor of 1.02, which is a 2% increase every year. So if I wanted a 5% increase, I would have like 100 times 1.05 to the power of t, so on and so forth. I don't need that there though, so get out of here. All right, looking at the graph for this is what we're dealing with. I can add a slider, which is kind of cool. And hopefully you guys just know the basics behind exponential graphing. If your b value, your factor, is greater than 1, it is exponential growth. And if it's if it's positive and less than 1, so it's like a decimal, like 0.07 or 0.05, it's exponential decay. We typically don't look at negative values, as you can see, not there. So between 0 and 1, it's exponential decay, and it goes down over time. And if it's larger than 1, it's exponential growth, and it goes up over time. So I'm going to erase this slider because I no longer need it. And I'm just going to put on Jessica's equation here, and I'm going to zoom out. I'm not going to utilize this lame old XY axis way. Maybe I will have to use it, though, a little bit later. Anyway, we have a part 2. Jessica's friend Tayshawn found an account that earns 2.5% interest compounded annually. Tayshawn made an initial deposit of $100 as well into this account at the same time Jessica made her $100 deposit. After 10 years, how much more money will Tayshawn's initial deposit have earned than Jessica's? Because what's going on here is that he gets more interest. So if this is Jessica's, Tayshawn's is going to be the same thing almost, but instead of 2% interest, it's 2.5% interest. So I'm comparing these two, and I'm finding how much more money, the difference between how much larger Tayshawn's amount of money is going to be versus Jessica's. So I graphed both of these on Desmos, of course. And as you can see here, so Tayshawn's in green and Jessica's in blue. He's much higher throughout our journey, right? And actually the gap widens more and more over time. So you definitely want to capitalize on either higher interest rates when it helps you or lower interest rates when it hurts you, right? And I have an x value of 10 here because I think we were interested in after 10 years, right? So let's look at that. After 10 years, Tayshawn is at, so I'm looking for the points of intersection, $128 and like a penny-ish. So I'm gonna be careful because SAT is very particular with rounding. So I'm gonna write down that whole value, and I'm gonna subtract off how much Jessica has, which is 121.899. 121.899. I get an answer of 6.109, knowing that this rounds up to a penny, right? So $6.11 is my answer for this one, 6.11. And I realized I didn't really actually go over the answer for 37. What is the value of x? It was 1.02. So the answer for 38 would be 6.11. Ending our little game of visualizing on the SAT. Could you have done this in another way? Just want to play around with that possibility. I like the graphical approach, I'll be honest. I think the graphical piece is key. You can actually graph it as, here's a fun thing you can graph it as. This is just me being extra at this point. I can subtract off Jessica's like inside of the equation. So remember, the point of this video has not been to show optimal solutions, but to learn off of the graphical elements to this. And we can see here, this is the difference. So I'm just concerned I'm concerned with what happens at 10. So this is just kind of coming off the top of my head. Here's that 6.109 value again. If I take the difference and I just figure out, well, if I plug in 10, what is the difference at 10? That's another way of playing around with it. I can just plug in the values as well. So I know the two equations, right? And I have a calculator. I can just plug in 10 into Jessica's. I can plug in 10 into Tayshawn's, and then I can just find the difference that way. A lot of different ways to approach this, but know what you're doing graphically because that can go a long way. Anyway, that is actually the end of this video. Hopefully you learned a little bit and built an intuition behind why the visual piece of mathematics is important to have. I'm going to continue to math on. I hope you do the same. I'll see you in the next video.